All right, great. Well, thanks. We're really happy to be here and present a bunch of the work we've been doing. In this case, I'm actually going to not talk about Mirror Lake specifically, but the Chubb River. But of course, they're nested together and they're strongly related because Mirror Lake is in the Chubb River watershed. And ultimately, what happens to Mirror Lake ends up coming through the Chubb. So it's definitely a relevant topic. So I want to acknowledge Elizabeth. She's my co-author on this, and we have a bunch of participants that have been helping us. Hunter, who couldn't be here, and Sean Regalado, as well as Brendan and Dan have been working on this project. Like Dan did, I stole this from him. He likes to start with the take-home message, so I'm stealing that from him. But what I hope that you see at the end of this talk is that the chemistry of the Chubb River is really significantly altered by de-icing agents. And I'm saying not just road salt applied to roads, but all kinds of de-icing agents that are applied to parking lots, fronts of stores, driveways, all kinds of stuff. And what this presentation will show is just how much the area around the village of Lake Placid is contributing to that. And the second take-home message I hope you get is that I want you to hopefully understand that the Chubb River is really an important sentinel for water quality impacts around Lake Placid area. All that water that interacts with the village ends up going through the Chubb. So it's really important that we develop a long-term monitoring program for the Chubb so we can understand how the changes we make, like those ones that were described by Mayor Randall, when we make those changes, we can actually detect them in the Chubb, so we should be studying it. So some of the objectives are, the main objective of this data analysis was to try to understand what Lake Placid's contribution is to the pollutant load of the Chubb River. And we're looking at lots of different pollutants, nutrients, road salt, sediment, but what I'm going to talk about today is specifically around road de-icers. And then the second objective is that studying the Chubb River really helps us at the AWI contribute to our larger regional understanding of what happens to road de-icers once they get put on the road. So Dan showed a bunch of data from some of our other streams. The Chubb River project that we're working on is contributing to that data set as well. In fact, it's a really good addition because most of the rivers and streams we monitor are much smaller systems with much smaller watersheds. The Chubb River is by far the largest one in our regional network. So just a little bit of background information on the Chubb. It's a 10,475 hectare watershed, or if you prefer English units, it's 25,833 acres. But as scientists, we like anywhere else in the world where things make sense, we like to use the metric system. So overall, the Chubb River is largely forested. So over 80% of the Chubb River is covered in forest, whether it's deciduous or hardwood forest. But it's a really unique watershed also because in the southern part of the watershed here, we have a really large tract of forest preserve that's draining the High Peaks Wilderness area where there's very little human impact. Up in the northern area, just north of Lake Placid, or around the ring around Lake Placid, is another large tract of forest preserve that's relatively unimpacted. But right in the center of the watershed, we have essentially an urban environment. It's crisscrossed by roads. It has lots of road salt going on, lots of lawn, lots of fertilizer application. It has a permitted wastewater discharge plant, which is permitted to discharge effluent into the Chubb. So in the center, there's lots of human impact going on. This figure also shows that in the Chubb River, about 7% of the watershed area could be classified as impermeable surface. That means it's roads, driveways, rooftops, parking lots. All of these impervious surfaces create runoff of road de-icers. So we took advantage of that unique system that's going on in the Chubb to establish two monitoring stations. One of the monitoring stations is right down there where that blue and pink triangle is. That's on Averyville Road, where Averyville Road crosses the Chubb River. So as the Chubb flows down from the High Peaks Wilderness area, it doesn't interact with very much human impact. There is some human impact on that southern end. There's Averyville Road, there's some houses, there's some winter road maintenance that goes on, but all in all, it's a relatively small contribution. So our first monitoring station, which we were going to refer to as the Upper Chubb River, it's upstream of the majority of human impact. And for the Chubb, it represents what we would consider to be least impacted condition for the Chubb River. And then our second monitoring station, we're calling that the Lower Chubb. This is right near the terminus of the Chubb River, very close to where it meets the Ausable. It's probably 500 feet downstream from the wastewater treatment plant. So the water that makes its way to that station has interacted with numerous human impacts. It's important to recognize, though, as I go through the results, that the Lower Chubb River encompasses the entire watershed. All of the water that flows through the Chubb River watershed makes it to the Lower Chubb. It's the whole thing. But the Upper Chubb is just that spot on the south side that's relatively impacted. A couple of the other features relative to this and to human impact and to road de-icers. Look at this table. So this compares the watershed area. So the watershed area of the Lower Chubb is much larger than the Upper Chubb by about a factor of 3. If you look at the amount of roads, the Lower Chubb has 139 kilometers of road crisscrossing through that central urban area. Most of those roads are what Dan classified as local roads, so they may receive a variety of winter road maintenance. Only about, I believe it's about 7 kilometers of that is New York State roads, both 86 and 73. The Upper Chubb, though, only has 14 kilometers of roads in it. So if you look at the density of roads, that is how much road exists per area of watershed, you can see that the Lower Chubb has about close to 4 times the road density as the Upper Chubb. And the impervious surface area. So the Upper Chubb has 7% impervious surface, where, I'm sorry, the Lower Chubb has 7% impervious, while the Upper Chubb is about 0.5%. So it sets up a good situation where we can really explore what the impact is in and around the village of Lake Placid. But, you know, Dan mentioned how important state roads are to the salinization of lakes, and that's true, especially on those larger scales, large lake watersheds, park-wide. But, you know, recognizing that in the village of Lake Placid, there's a lot of other sources for road de-icers and salts than just state roads. We have state roads, obviously, but there's also a large amount of parking lots. And I was thinking about that today when I was struggling to find a parking spot out here. We've got a bunch of salting that goes on in front of storefronts, on driveways, in front of people's homes. And we also have permitted discharge from the wastewater treatment plant, which undoubtedly also contains some amounts of salts. Not because it's road salt getting in there, but because there's a lot of salt in our diet, in our food sources, and the water's chlorinated as well. So what we did at these 2 stations is we established these 2, I'll say, semi-permanent monitoring stations. We're set up on both the Upper and Lower Chubb. What we did there is we installed some data loggers. And there's a picture of the 2 data loggers we installed at each station down there. The first one is what's called a level logger. It's a pressure transducer. That's what's the picture on the right. And we installed that into a PVC pipe that was either anchored on rebar or installed into the banks of the river. And what that does is it measures the pressure change as the water goes up and down in the Chubb. That is related to the height of the river. So this allows us to measure how high the river is every hour. And the height of the river is related to how much water is going through there. So it gives us an understanding of how much water is coming through the river at both locations every hour. We also installed a conductivity meter. So the conductivity meter measures the electrical conductance of water. So, you know, despite what you think you know, water is actually a really poor conductor of electricity. It only becomes a good conductor of electricity when it has dissolved ions in it. So the more dissolved material, more dissolved ions, like salt, the greater the conductivity of the water. So this allows us to understand how much dissolved ions are in the water at every 60-minute intervals. So if we want to look at what the Lake Placid region's contribution to pollutants is, we have to be able to estimate what the export is. So we're interested in knowing how much salt is being exported from the upper Chubb. It's the total amount of a substance that's lost from a watershed per unit of time. And that substance can be anything you're interested in, depending on the question. It can be sediment. Like that was a really popular thing to study in agricultural areas, looking at sediment loss. So you could look at nutrients like phosphorus and nitrogen, or you can look at road de-icers, or in our case, we looked at chloride, a main ion in road salt. In order for us to calculate how much is being exported, we have to do a couple things. The first thing we have to do, so step one, is we have to quantify how much water is coming out of the watershed at both of those locations. So that's what my colleague Liz is doing in this upper picture. She's measuring the discharge at the upper Chubb. And we do that with a discharge meter. This picture right here shows the dangerous end of the discharge meter underwater, and that's a Doppler radar discharge meter, so it's a very high-tech way of quantifying how much water is coming out. So we have to do that. And we did this on a regular basis. We've done this over 30 times in the last 20 months at both locations. The other thing we need to do to get at that export number is we have to figure out how much pollutants are in the water. So it's the concentration, in this case, the concentration of chloride in the water. So we take a water sample, bring it back to the lab. One of our coworkers here, Hunter, is setting up some of our analytical equipment to analyze chloride. So now we know how much water is coming out of the watershed, and we know how much chloride it's carrying. That's how we get at load, the total amount coming out of the watershed. And then the third step then is we need to combine that data from the field and from the lab with the outputs from those data loggers we stuck in the stream. So we go out there, we download them, and that has information on how much water is moving through the rivers and the conductivity every hour. So now we've been able to convert our 20, 30 trips, and we can correlate them together and produce data for every hour. So let's look at some of the results that we generated from this. So the first result I want to show you is how well we are able to quantify how much water is coming out of these two watersheds. So we've got the upper Chubb here and the lower Chubb, and the graphs on the right are what are called stage discharge curves. So the way that works is on the x-axis here, this is the x-axis, we have stage height in meters. That's how, think about it as that's how deep the river is. So the deeper the river, the more water is coming out. And on the y-axis here, we have our discharge calculations, which is an actual how much water is coming out that we measured. So we're able to build this relationship between the height on those data loggers and the discharge. And both of these are really fairly good stage discharge measurements. So what that allows us to do now is take all those stage heights that have been collected every hour for 20 months and convert them to actual volume of water coming out of the river. That's how we get at that first step at export. This is the relationship we got from the data loggers when it comes to how the conductivity of the river. So for the upper Chubb here, here's the conductivity coming off of the downloaded data loggers, and here's the chloride concentration that we got in the lab. And you can see there's a fairly good positive relationship for both the upper Chubb and the lower Chubb. The lower Chubb relationship is much stronger than the upper Chubb, but if you look at the upper Chubb's chloride concentrations, we're in the range of 0 to 2 here. It's a very small range of chloride. And that goes back to what Dan said, is because the chloride levels in the upper Chubb are very low because there's no source. The only source is deposition from the atmosphere. When you look at the range of chloride at the lower Chubb, it goes up to about 60 or 70 milligrams per liter. So we have a much bigger range to develop it. So what this allows us to do is figure out how much chloride is in the water every hour, even though we were only out there 30 times. So now we can combine all this to make some estimates of what the export is from these two stations in the Chubb. So I'll go through these results. The first result I'm going to show you is just the conductivity. So how much electrical conductance there is in these two watersheds. Remember that the more dissolved ions, the greater the conductivity. So on the x-axis, I've got the different months. It's 2016 and 2017. And on the y-axis is the conductivity. So first I'm going to show you from the upper Chubb. So here's the upper Chubb's conductivity. Every 60 minutes, for nearly 2 years. And you can see it does fluctuate a little, but it's relatively low. The Chubb River conductivity in the upper portion, upstream of the village, is typically around 20 to 30 microsiemens, which is a fairly low-level conductance, but it's similar to what we see in other streams that have no human impact. So let's think of it as sort of like a baseline. And then here's the conductivity for the upper Chubb, just downstream from the village of Lake Placid. So obviously, it's much higher. It typically ranges around 150 to 200 microsiemens per centimeter, so quite a bit higher in conductance. And at times, the conductivity can be even up to 600 microsiemens per centimeter. So you see these big spikes in conductivity. Typically, we see those in the winter and in the spring when we get a snow melt, which rushes all that salt-laden water off the roads and off the parking lots and driveways in the village, and they make it into the Chubb. You know, and I've seen this happen. We've all seen it happen. Like if you sit at Lisa G's and you look at that big culvert under the road, sometimes that is just blasting out road runoff right into the Chubb River. That's what causes these spikes. One thing that's really interesting is look at the far right side of the graph, which is May, June, July, August, September, October. You see, just like Dan pointed out, even in the summer months, the conductivity increases. So that's probably because of a couple things. One is the Chubb River's water is much lower, so it's more concentrated, and it's also, we're seeing groundwater interaction and groundwater making it to our data loggers. And it could also potentially be increased export from the wastewater treatment plant with the busy summer season, because the wastewater treatment plant almost certainly exports some chloride as well. We don't at this time have a handle on what that is. So in terms of just conductivity, the magnitude of Lake Placid area's impact on conductivity is that the conductivity downstream from the village of Lake Placid on average is 100 times greater than upstream of the village of Lake Placid. And at times it can be 600 times greater. Now I want to look at the total export. So the total amount of chloride that comes out of the Chubb River. We're going to compare the upstream of Lake Placid to the downstream again. So this time we're looking again at the dates and the years. And on the y-axis, this time we have chloride export. And I'm expressing it this time in tons of chloride per day. That's right, tons of chloride per day. So here's the export from the upper Chubb. You'll see those little tiny black lines. That's export every day over those 2 years. Really small export of chloride, as we would expect, again, because there's no source. The only source is atmospheric deposition of a small amount of chloride that makes it into the atmosphere when volcanoes erupt and things like that. So it's typically around 0.2, 0.3 tons of chloride per day. Here's the export from the lower Chubb just downstream of the village of Lake Placid. So quite a bit different, substantially more chloride. And as you can see, there's a big spot missing in January through March of 2017. We don't have data for that from the lower Chubb, which is incredibly disappointing, but our stage recorder that measures the height of the Chubb was damaged by ice, and we didn't know it was damaged till we went back in May to download it. So unfortunately, we don't have data for that section of time. So really, this figure that you're looking at is very conservative, because we don't have data for this winter and spring when the export of chloride is going to be by far the highest. But the export just below the village ranges anywhere from 1.5 tons per day to as high as 8 tons of chloride moving through the river in 1 day's time. So in terms of the magnitude of the impact that Lake Placid area has, on average, the Chubb River is carrying 96 times more chloride after it passes through the village of Lake Placid than it did upstream of the village. And at times, it can have up close to 200 times more, 171 times more chloride on certain occasions in the winter and spring. That's a tremendous amount. It's kind of hard to wrap your mind around that, but this is really a conservative view because, again, we don't have data for the saltiest time of year. This is really sort of the same figure, but this time I've done something that we do when we're looking at chemical cycling through the environment or trying to understand export is we have to correct it for the southern watershed. And those watersheds vary greatly in size. You have to make a correction. Because as a watershed gets bigger and bigger and bigger, it's going to carry more water and it's going to export more material. So what we've done in this figure is we've taken that chloride export and we've divided it by the size of the watershed so that we can express the export in grams of chloride for every hectare of watershed per day. Now we can compare apples to apples. The story is the same. The lower Chubb exports substantially and significantly more sodium. But you can see the upper Chubb's numbers increased a little bit because we corrected for its small watershed size. So when we take in that, what we call aerial export or export coefficient, and we correct for the size, the export of chloride downstream of Lake Placid is 20 times higher on average, or up to 52 times higher on occasion. So, in conclusion, so I promised Brendan and Kelly that I would make up for running a little late, because my presentation was pretty short. Our preliminary results, I think they clearly demonstrate the magnitude of impact that the area around the village has on the export of chloride. So when we apply salt to the roads or to our driveways, our walkways, it all eventually is going to end up running into the Chubb. And the magnitude of that is great. We see an increase in units of tons coming out of the Chubb River. So not only is this an important issue for Mirror Lake, as we'll see with Brendan's talk, for the Chubb, but ultimately for the Ausable and for Lake Champlain too. There's a large contribution to chloride. Another thing that's really important, I think, about this study is that, we think about the history of Lake Placid and anywhere. Lake Placid has and continues to impact the environment. It's just the nature of humans and what we do to the places we live. Looking at this picture even from 1885, this is the sawmill on Mill Pond, right at the Chubb River by Lisa G's there. But the Chubb River is really uniquely positioned because, as I mentioned at the beginning of the talk, it can really serve as a sentinel for the changes that are going on in the Lake Placid area, whether they're positive changes or negative changes, whether they're changes across the watershed, so changes in space, or whether they're changes we make over time. We can detect those changes in the Chubb River. And because of that, we really strongly feel that efforts should be made to make sure that we continue to monitor the Chubb River on a regular basis and ask the right questions about what's going on so that we can detect the changes that we're going to make and that we're already making around the Lake Placid area. So I just want to acknowledge that we're working with the Ausable River Association on this, and actually Ausable River Association got funding from the New York State Department of State for this project, which then they funneled to the AWI to do some of the field work and the lab work. So is there any questions?
Yeah, for Chris.
Yeah, Corey, great presentation. Your results are disturbing in the sense they imply groundwater contamination by chloride in the summer. But you said there might be some contribution from the sewage treatment plant. Have you thought about having a monitoring station upstream of that?
Yeah,
or do you have a sense of how much contribution that might be?
We don't have a sense. I have no idea. I know that there's close to 1 million gallons per day coming out of the wastewater treatment plant, but we don't know what the chloride concentration is. So yeah, we've been speaking, and Brendan and I have been talking about perhaps installing another station or perhaps trying to get some data from the wastewater plant. They don't monitor for chloride. So I think it's a possibility. Like at Paul Smith College, we have a wastewater treatment plant, and its concentration of chloride is usually 20 milligrams per liter. So it's probably higher in Lake Placid, but we just don't know. But yeah, it does imply that there's some groundwater contamination, and that follows what we see in a lot of other streams in our regional network.
Corey, good stuff. Just as a side note to that, we've monitored a couple wastewater plants around Lake George and have found, now all their effluent has to be subsurface discharge But our monitoring wells have found that the Lake George plant was about 48 milligrams per liter, so that gives you an idea. Secondly, you talked about potential influence from private properties and not just roadways. Do you have any idea on that application or runoff from those, or is that something we're trying to find ourselves?
Yeah, I know that you're working on that. We don't have any, I don't have any real understanding of what it is. And what we've been thinking about recently, and by that I mean this morning, or keeping it fresh, it's just, is parking lots.
Yeah.
Because they're maintained usually by a private plowing company, and, you know, even my experience with parking lots is there tends to be an excessive amount of salt applied. So specifically in the village of Lake Placid, that probably is a significant contribution other than just the roadways.
Our guesstimate, and from our work with organization SIMA, Snow and Ice Management, is it's about 50-50 almost. Roads versus private, so. But we haven't confirmed that.
Yeah, we know there's a significant contribution because if we sum up the amount of chloride coming out of the Chubb on an annual basis, it's incredibly high, and the number is high enough that we can't really make it work with just application on state roads. It's nowhere close. There's definitely more salt coming through the Chubb than state application rates. So then that's plowing on the local roads, but also some of the other sources. All right, thank you.
Thank you.